Unit 2, we are going to start a new unit. The unit title is Constraint Satisfaction Problem. That means it is like a searching algorithm to find the one solution. So we assume there are multiple solutions, but we are going to find a solution by using constraints. So there are some restrictions. To solve constraint satisfaction problems, what we are going to consider is we need to define the problem first by deciding set of variables. So we are going to solve for the variables when all the variables has one satisfied value. That means we are done the problem solving. Then to solve the problem, you have to have domain. So each variable will have its own domain. I don't know where I put, but yeah. And constraints are there. So you have to find each variable has a value that is the goal that satisfies all the constraints on the variables. So there is a miscellaneous problem. T, W, O, F, U, R are used. And we already know because we practiced the SAT problems. If we use letters, that means each letter represents one digit number. Also, in this case, any number is not leading by 0. So if I start from the variables first, so all the letters we used, so T, W, O, F, O is already used, so only U and R. Then domain for each one, domain for each digit. I can say 0 through 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then very first constraint I can say is all variables, each variable has one digit distinct because it cannot be the same. Whole number because 0 is inclusive. There are more constraints because it's addition. So I can add more constraints. O plus O is R. But it can be more than 10, so I can make hidden variable C1. So C1 times 10 plus R. Then second constraint, I can say now C1 plus W is, now I'm going to make another hidden variable C2. So C2 times 10 plus U. Now C2 plus T is C3 I'm going to make now. C times 10 plus O. C3 is F. I said no leading by 0. No leading 0. That means C3 and F are 1. So these are all constraints. And also, all variables have one digit distinct whole number. We can also change this one too. But like O is not the same as W. O is not the same as R. O is not the same as W, not W. T. Then O is not the same as U. O is not the same as F. Then you can also work W is not the same as U. W is not the same as R. You can list all of them too. When you write the code, you probably will write this in color one. Now we are going to think about how to visualize this problem. So we can draw constraint hypergraph. Hypergraph means one edge can have multiple vertices. So usually when we have a graph, when I have A to B, each edge has only start and end. One start and one end vertex. Only two vertices are related. But now, for edge, we can connect multiple vertices. I can say T, W, O, F, U are also hidden variables C1, C2, C3. I can say O plus O R and C1. So O R C1 can be connected in one edge. Then C1 W U C2. C1 W U C2 can be connected in one edge. C2 T O C3. C2 T O C3 in one edge. And also C3 and F is one edge. Complicated, but this is the hypergraph. So we are going to represent this hypergraph in a little different way. The O, variable O, is connected to R together. So in the first edge, edge 1, we'll have variable O and R. Then the hidden variable C1 is connected. So that's the first edge. Then second edge, we'll have C1 W U C2. So in the second edge, I'm going to have W and U connected and C1 and carry 2, C2. Then third edge, we connect C2, T, and O. Now fourth edge will be, this one as a result is C3, so C3 is also connected to the edge 3. Edge 4 will have C3 and F. So when we solve the problem, we can think about the edge with lowest number of the vertices connected and extend it. I'm going to rewrite this situation. Now I'm going to try to solve really by using this one. Oh, I forgot to write hidden variables C1, C2, C3. So I'm going to write down and the next to the variables, hidden variable C1, C2, C3. Then hidden variables domain will be its carryovers only 0 or 1. I'm going to list all the variables. So when I program it, I'm going to define all the variables what I need. So for each variable, I'm going to think about the domain. So domain for T, domain for W, domain for O, domain for F, domain for U, for R, then C1, C2, then C3, domain for, domain for, domain. Domain for C3 and F are already done. They have 1, so they are done. Domain for C1 and C2 are simple because they have 0 and 1. T through R, they should have least number. That means if 1 is already chosen, other variables cannot use 1. So I can say, so for each other ones, I can have all the rest of them, but T are leading. So T cannot have 0. So 2, 3, 4, 5, 6, 7, 8, 9 are candidates. For the W, 0, 2, 3, 4, 5, 6, 7, 8, 9. For the O, 0, 2, 3, 4, 5, 6, 7, 8, 9. And U, 0, 2, 3, 4, 5, 6, 7, 8, 9. For the R, 0, 2, 3, 4, 5, 6, 7, 8, 9. Actually, by using the constraint, I can reduce some. I can eliminate some. First one is O plus O. 2O equals E1 times 10 plus R. 2 times a number, 2 times O is even number. Even is even plus even because 10 times a number is even. That means R must be even. So in the R, any odd number I can take out. Also, if O is 0, R is also 0. So O cannot be 0. But R can be 0 at this point. If O is 5, or 5 plus 5 is 10, so R can be 0. Now the second one I can also look at is C1 plus 2 times W equals C2 times 10 plus U. And another one, C2 plus 2 times T equals C3 times 10 plus O. And C3 I don't need to worry about. Still, there are so many vague things. So it looks like there are not only one way to solve. So now I'm going to think about some techniques. There is a backtracking search. That means you are going to choose one value, then if it does not work, so just following the one direction like a depth first search, then if it does not work, come back to the previous state. And for the checking is one by one you are going to try. Then minimum remaining value is when you choose a variable to work on, you are going to choose which has fewest legal values. Okay, so I'm going to try that. MRV, I'm going to choose a color. So if I use MRV, minimum remaining value techniques, I probably choose C1 or C2, which has only 2 candidates. Then I may take the first one, like for the checking. I'm going to choose 0 for C1. If I choose 0 for C1, this part is gone. That means 2 times O equals R. That means R is only 0, 2, 4, 6, 8. So O can be only 0, 1, 2, 3, 4. But O cannot be 0. So R cannot be 0. If O is 2, because O cannot be 1, 1 is already taken. If O is 2, R is 4. So R cannot be 2. If O is 3, 6, 4, 8, and O cannot be 5, 6, 7, 8, 9, because there is no carryover. So now O has only 3 candidates. R also has only 3 candidates. Another thing I can take out is C1 at the second constraint. Now C1 is 0 because I plugged in. In that case, 2 times W, so even number equals even plus U must be even now. So in the domain of the U, any odd number will be out. I think with C1, I did all the constraints. I satisfied all the constraints. Now I need to go back and look at the next variable to work on. And I look at everything. Yeah, still C2 has minimum remaining values. So I'm going to go to the C2, then choose first one. Now C2 is 0. I'm going to go back to my constraints. If C2 is 0 in the second constraint here, now W and U can be restricted. So 2 times 0 is 0. W and U cannot be same value, so 0 is out at both. Then if W is 2, U is 4. So U cannot be 2. Then W is 3, 6, W is 4, 8, and W cannot be 5, 6, 7, 8, 9. Because if W is 5 or higher, there is a carryover, but it says carryover is 0. Now C2 is 0. Already know C1 is 1, C3 is 1. So I can rewrite 2 times T is 10 plus O. Now let's see. O has 2, 3, or 4. But it's even equals 10 is even number, so O must be even number too. So O cannot be 3. Then if O is 2, that means T is 6. If O is 4, T is 7. That means T is only 6 or 7. Every other values are out.